Thanks, James. Hi, I'm Eno. I'm going to talk today about IOFlow, software-defined storage architecture. I'd like to thank first the co-authors of the paper, Hitesh Balani, Greg O'Shea, Thomas Karagiannis, Anthony Rostron, Tom Talpi, Richard Black, and Timothy Zhu. So I'll start by giving a little bit of background and motivation for this work. The target environment for this work is enterprise data centers. So we're shifting gears slightly here. So inside of these data centers, you tend to have compute and storage servers. You tend to run general purpose applications. And it's not uncommon for these applications to run on multiple virtual machines. So for example, the red application there is running on a set of 2 virtual machines. You tend to have a separate network for VM to VM communication as well as for VM to storage communication. And it's the latter that's going to be the focus of this talk. Storage is usually virtualized. What does that mean in practice? It means that the VMs are often presented with a virtual hard disk, which tends to be just a large file stored inside the storage backends. And the resources, both the storage network and the storage backend, are shared among each of these tenants. So with this background in mind, the motivation is straightforward. The tenants want predictable behavior and performance in this shared environment, as if they had their own dedicated resources. They want performance guarantees, and they also want control over the services processing their data along the I/O stack. Now, the problem is the data centers today cannot provide those guarantees and control. To see why, let's go through an example. So this is a simple example where we have to provide guaranteed aggregate bandwidth, B, for the red tenant, again, running on 2 different machines. If we zoom in here at part of the storage stack, the client side, we see something interesting. The application runs inside a virtual machine. The virtual machine itself has multiple services. It has an operating system, it has a file system, it does caching and scheduling. Then you have the hypervisor with additional services, such as the I/O manager. It can perform things like replication and scheduling as well. When the requests arrive at the storage server, you have, again, file systems. You might have layers like deduplication. And again, you have other layers such as caching and scheduling. So it becomes pretty clear that we have a deep I/O path here with 18 or more different layers providing different services. And today, all of these layers are configured and operate independently. Not only that, but there is also no understanding of the application performance requirements in each of these layers. Applications today don't have any way of expressing their SLAs. For example, you don't open a file specifying how fast you want to read or write to it. So sharing resources today basically means living with interference from the neighboring tenants. So for example, the blue application can be aggressive and consume most of the storage bandwidth. So it's this interference that causes the applications to have unpredictable performance. At this point, you might be thinking, well, we have networks as well here. We have some switches, and we have had techniques like software-defined networking to handle this complexity. So what's different about the storage stack? A couple of things are different. So first of all, we don't have a storage control plane today that can coordinate each of these layers' configuration to enforce an SLA. Each layer has its own configuration and makes its own decisions. Second of all, we have set a high bar for the SLAs we want the system to meet. So we want detailed SLAs. We want aggregate across VMs, files, and storage operations. Now, aggregation is challenging because it adds a further distributed dimension to the configuration problem. You have to also configure the layers across the various different machines. We also want non-performance SLAs. We want full control over the services a tenant has over the I/O path. And finally, we want to support unmodified applications and VMs for maximum impact. So IOFlow is the architecture we're proposing. It decouples the data plane, which is the enforcement, from the control plane, which is the policy logic. At a high level, it looks like this. We have SLAs specified by either tenants or data center administrators. And these SLAs are sent to a controller. The controller is logically centralized. It has global visibility over the entire system. And then the controller, through the IOFlow API, is going to enforce a given policy by configuring each of the independent layers. So in a nutshell, in each of these layers, we have to have an enforcement mechanism, and the enforcement mechanism we have chosen is queues. So by controlling the queue functions, we're going to be able to enforce a given SLA. The contributions of this work then are we've defined and built a storage control plane. We have controllable queues in the data plane. We have also specified the interface between the control and data plane, which is the IOFlow API. We have also built several centralized control applications that demonstrate the power of the architecture, as I'll show in the talk. Let's start with the SLAs. IOFlow supports a flow abstraction described using 4 parameters. So initially, the source set is a source made of a set of VMs. So you can specify here a number of VMs. Then we have a number of file operations again in this set. Operations in storage are things like reads and writes. Then we have a destination set made up of files and shares, which you can think of as just folders or directories, collections of files. Let me go over a couple of examples. So here's an example where a tenant running on VM 1 to 100, so these are 100 VMs across potentially multiple compute servers, specifies two kinds of SLAs for its workload. The first one says that its write requests going to a share that might contain, say, database log files, transactional log files, should have high priority. The same tenant wants the reads and write requests going to the database data files, okay, to have a minimum bandwidth requirement of 100,000 IOs a second. It's a minimum requirement. The system can do more if underutilized, and the tenant is indicating here that they are willing to pay for more if the system can actually do more. We also want non-performance SLAs, for example, path routing. The data center administrator for a trusted VM, VM1 in this particular example, can specify that this particular VM's traffic can bypass a malware scanner because it's trusted inside the system. The IOFlow API is the API that we have chosen at the low level to implement and enforce the high-level specification we mentioned in the previous slide. So there are three key functions that IOFlow provides: classification, queue servicing, and routing. So the first one is classification. We take an IO header there in each of these layers that implements the API, and then we put it to a particular queue. So the idea here is, for example, that the red packets are going to the red queue, and the blue ones are going to a separate queue. Then we have queue servicing. For each of the queues, you specify a token rate parameter. How quickly do you want the request to actually be drained from this particular queue? Also priority. How do you want to treat different queues with respect to priority treatment? We also have a queue size parameter. If the queue reaches the queue size threshold, then the queue notifies the controller and blocks any further inserts inside the queue. Now it's important to pause here and notice that there is no support in the IO stack for dropping IO requests, but there is support for back pressure, and the queue size parameter makes use of that. The third call is a routing call. For every queue, you can specify the next hop. So here we can see that the requests from the red queue are bypassing the malware scanner driver and moving on to the next queue inside the system. So there are two storage-specific technical challenges I'd like to spend a little bit of time talking about. They have to do with classification and also rate-limiting storage requests. So the first one is classification. So we talked about the SLA specified using the high-level names, but the layers, unfortunately, observe different low-level identifiers or IO headers. Now, for concreteness here, we move to a concrete storage stack inside Windows. Other OSs have similar storage stacks as well. And we see here the VMs running on top of the hypervisor, and on the other end, we have the storage server. Now, inside the guest file system, we see that this shared data set part of the SLA is only seen as a block device. So whereas the tenant wants to read and write from a particular data set and wants a guaranteed bandwidth B from it, the file system inside the VM has no idea what shared data set really means. It can only see a drive, for example, the Z drive, mapping to a block device. Similarly here inside the hypervisor, the SMB layer, which is SMB is file system protocol for remote storage, it can only understand request header entries of the type server and file name. So this particular file.vhd, VHD is for virtual hard disk file. On the other end, on the storage server, we have a similar story. The storage server understands volumes, for example, the H volume, and files, like the VHD file. And finally, when the requests arrive at the storage device, we have the block device, which understands things like device SSD5. And by the way, the same problem, this lack of the common IO header, holds true also for the source. By the time requests from VM4 arrive at the storage server has no idea where they came from. Okay? So the VM name is also lost. So how are we going to deal with this problem? We want each of the layers to enforce an SLA, and yet we have this mismatch. So we deal through this flow name resolution through the controller. The idea is that the layers are going to expose the IO headers they understand to the controller, and then the controller is going to map the SLA to layer-specific IO headers. Taking an example here, the SMB layer tells the controller that it can only understand two entries in the IO header, the VM security descriptor, and also a server name and a file name. And subsequently, the controller, if it decides to actually place a queuing rule inside the hypervisor, is going to use only those fields in the IO header. Here we have an example where we're creating requests classification, putting them on a particular queue, Q1. and then we're setting a token rate for that particular queue. Now, when do you install this rule? You install this rule whenever the file is first opened. The queuing rule is maintained then as part of the file handle, and any subsequent IOs on that handle are going to obey the rule. So the controller is not on the IO data bed in this particular case. So this was the first problem. Moving on to the second one, which is rate limiting for congestion control. Rate limiting is very important for performance SLAs. Today we don't have any storage congestion control mechanism in place. To understand why rate limiting is important, a simple example of an aggressive tenant that just sends too many requests to the storage server, overwhelms it, and prevents it from meeting the SLAs of the other tenants. Now, the algorithm that we borrow from the networking community is the standard token bucket algorithm, which works by outputting incoming packets as long as there are enough tokens inside the system available. So the way to control the rate is by controlling the rate of the tokens that you actually put inside the system. However, applying the token bucket algorithm to storage for rate limiting storage requests turns out to be challenging. We're going to look at one example, a simple one. How do you rate limit two VMs, one of them reading, one of them writing, to get an equal share of the storage bandwidth? A simplistic view here with the two VMs. We have the storage server. Both of them, for simplicity, are doing 8K reads and writes. And we'd like at the storage server to see something like those queues over there, where there is an equal share between the bandwidth. Now, if you do rate limiting at the hypervisor based on the payload bytes, like the network would do, unfortunately that wouldn't work. And what you'd see inside the storage server is this. So the red packets would dominate. The reason is because read requests at the hypervisor are very small in size. Right? In fact, it's just the I/O header as such, whereas write requests contain the full payload of the system. So you just send many more reads than writes. Now notice here that requests cannot be dropped on the storage stack, unlike in networking. So a key congestion signal that we used to have in networks, we don't have it for storage. So once the requests enter the storage server, the server is committed to completing them. And therefore, the SLA on the blue VM is actually not met. You could do a little bit better than rate limiting on payload bytes. Remember that we have the full I/O header at the hypervisor stage. So you can rate limit based on the real bytes that are actually going to be read from the storage server. And that would work in some cases, but there are other cases where that doesn't work either. So it's a step in the right direction. But for some devices like SSDs, for example, writes could be more expensive than reads, perhaps by an order of magnitude or more. And then we'd have the opposite problem, where the write requests would actually dominate the bandwidth of the storage device. The third option would be to rate limit based on the number of IOs a second. So you picked one read per write, so that's called rate limiting based on IOPS. Unfortunately, it doesn't work if then your red VM starts changing its workload and uses larger request sizes. So in this particular case, the red VM using 64 kilobyte requests overwhelms, again, the storage system. Now, it's clear at this point that we need to do the rate limiting based on the true cost of the operation. One way we use the controller to do so is by having the controller there. We have global visibility of the topology map inside the system. The controller knows when new devices are added or removed, and the topology of how requests flow inside the system. And through what's called the discovery component, it constructs empirical cost models based on device type. We have models for memory, in-memory systems, SSD-based systems, and also disk-based systems, and constructs them based on several workload characteristics, such as read-write ratio or request size. And then the cost models are then assigned to each of the queues through one API in the IOFlow set of APIs, which is configure token bucket. An example cost model, for example, would say consume 2 tokens for 64 kilobyte requests, but just 1 token for 4 kilobyte requests. We have the additional problem that storage requests tend to have, at least theoretically, unlimited request sizes. There is nothing to stop them from, say, being 1 gigabyte or more. We also split large requests efficiently without impacting performance to allow preemption inside the system. So I'd like to summarize things so far. So we just talked about parts of the IOFlow API, classification, servicing, and routing. And the main takeaways there is that when it came to classification, metadata that used to be private to each of these layers is now exposed to this controller, and the controller is out of the critical path. When it came to servicing, we needed to do congestion control based on the true operation cost. So these are the changes on the data plane. Not all the layers are expected to implement all of the 3 calls. They can implement none of them. They can implement a subset of the calls. Once we have this API in place, then the question is, how does the controller enforce one of these end-to-end SLAs? So for that, we're going to switch gears. We're going to move on to this SLA here, where we have the red VMs from 1 to 4, accessing, reading and writing from a particular data set. For simplicity, I'm just only going to talk about aggregation across VMs. Of course, in practice, VMs in practice would read also from multiple storage servers, but let's keep aggregation on the source only for the example. Now, the tenant wants a fixed bandwidth of 40 gigabits per second, and it's clear at this point that the SLA needs per VM enforcement. We need to control the aggregate rate of each of these VMs that reside on potentially different physical machines. So at this point, you can do static partitioning, so you can divide 40 by 4 and assign each of the VMs 10 gigabits per second. That's suboptimal. To see why, if 2 of the VMs go idle, we'd still like the remaining 2 to get 40 gigabits per second. If you do the static partitioning, they only get 20 gigabits per second. So in practice, we want what's called the work-conserving solution, where VMs with traffic demand should be able to send as long as the aggregate doesn't exceed 40 gigabits per second. There is an algorithm which is known as maximum fair sharing that does exactly that. It's a well-developed algorithm in the network community. Its existing solutions tend to be distributed and tend to rely on congestion control signals that do exist in the networking stack, but again, don't exist in the storage stack. However, we have a centralized controller, so what we have done is we've converted the distributed algorithm into a simple one that runs inside the controller. How does it look like? Well, here we have the controller. Every interval S, it samples statistics from each of the VMs, after first, of course, classifying their traffic. It then uses centralized max-min fair sharing both within a tenant for the VMs that belong to a tenant and also across tenants. So we have max-min fair sharing and work conservation in inter-tenant and intra-tenant as well. And then at the end of the day, it also sends the VM token rates for each of the VMs after running the algorithm. It can also choose the best place to enforce the policy. And remember, we have multiple layers inside the system. Each of them could potentially implement some of these queues. So you can think of the enforcement problem, deciding where to enforce, as an optimization problem. Ideally, you'd like to minimize the number of times an IO is actually enqueued. We're operating here with very fast networks and storage devices, 40 gigabit per second and higher. So it's clear that the impact on the data plane is going to be proportional to the number of times that you're actually queuing a packet. There are also certain SLA constraints as well. So for example, queues should be in place whenever the resources are shared or multiplexed. In practice, that means that bandwidth tends to be enforced close to the source. Other performance policies, such as priority, need to be enforced throughout the storage stack vertically as well. So in this particular simple example, the controller simply enforces at the hypervisor, but there have been cases where you need enforcement at all hypervisors and storage servers as well. So the main takeaway so far is that the centralized controller in software-defined storage allows for simple algorithms that focus on SLA enforcement and not on distributed system challenges. So there is a strong analogy here to software-defined networking, or SDNs, but storage came with its own set of SLAs and its own set of challenges as well. I'd like to talk a bit about the implementation. So adding the IOFlow API to all the layers I mentioned in the previous slides is ongoing work. We've added it to a couple so far. There are 2 key layers which are going to be important and relevant for the evaluation. They are the layers inside the hypervisor, the SMB layer, the file server protocol there, and also the one, its counterpart on the storage server side. These 2 layers are going to allow us to implement interesting performance SLAs for VM to storage traffic. When it comes to routing SLAs, we have also implemented the IOFlow API in a scanner layer. This is a scanner driver inside the kernel, inside the storage server. Requests can go through it or can choose to bypass it, depending on their classification and routing rule. We also have a user level stage where requests inside the kernel can actually be sent to user level for further processing, and then they are sent further down again. We've also implemented this for a network driver and the guest OS file system, and those points are made in the paper. So the map for the evaluation, we're going to look at 2 things. IOFlow's ability to enforce an end-to-end SLA. We're going to look at bandwidth SLAs in the talk. In the paper, there is a mix of bandwidth and priority SLAs and also routing applications as well. We're also going to look at the overhead in the data plane and the control plane of meeting the SLAs. So the setup is going to look like this. I know it's a little bit dense here. We have 10 clients, 10 physical machines running the hypervisors. We have 4 tenants, the red, green, yellow, and blue ones. There are 30 VMs per tenant, and they're all nicely load balanced around each of the 10 hypervisors, which means that there are 3 VMs per tenant per server. For those of you doing the math, there are 12 VMs then per server. We have a Mellanox 40 gigabit per second RDMA over converged Ethernet full duplex storage network in place, and 1 storage server using the SMB3 file server protocol with 3 types of storage backend: memory-based, so this is an in-memory file system, SSD-based, and disk-based. So in this evaluation here, we're going to show the RAM-based backend for 2 reasons. It shows IOFlow can enforce high-performance SLAs, and it also tends to bring the worst-case data plane overheads in doing so. The results for the other 2 are going to be in the paper. The controller runs in a separate server as a separate service. It has a 1-second control interval in this evaluation, and that's configurable. The workloads we have real I/O traces from Hotmail, the email service, from 4 of its tenants: index, data, message, and log. These are all standard enterprise data center types of workloads: file-based, database workloads, and also log transaction workloads. We're going to use the real I/O traces for trace replay on SSDs, and those are in the paper. We needed to scale them up for running them with the RAM-based backend, so we use IOmeter, which is a well-known file system benchmark, and we parameterize IOmeter with several characteristics from these traces, such as the read-write ratio and the request size, as you can see in this particular table. We then have 4 tenants with different storage bandwidth SLAs, as seen here. Again, these SLAs are aggregate over all 30 VMs for each of the tenants. They're all accessing 1 storage server. The tenants have different workloads, not only in the read-write ratio and request sizes, but the red tenant is also aggressive. It generates more requests per second in a closed loop, and it tends to want to consume more bandwidth than it's actually paying for, which is 800 megabytes per second. So the things to look for here are 3. So we're going to have distributed enforcement across the 4 competing tenants, where we're going to keep the aggressive tenant under control. Then we have the cases of inter-tenant work conservation and intra-tenant work conservation as well. So starting with the system in phase 1 with IOFlow disabled, on the y-axis is performance in megabytes per second, ranging from 0 to around 6,500 megabytes per second. So it's clear here that the red tenant is aggressive. It's consuming around 5,000 megabytes per second when IOFlow is disabled. At that point, we turn on IOFlow, and the controller notices the red tenant's performance. And in the next stage, which is shown here, it's going to configure around 120 queues, 1 for each of the VMs, to actually meet the SLAs for each of the tenants. There is a little bit of bandwidth left over for those of you that calculated all the SLAs and added them up carefully, and the remaining bandwidth is given proportionally to each of the tenants, including the red one. The next 2 stages are cases when we're going to have one of the tenants go idle, in particular the red one and the green one respectively. And these are examples where the controller notices that there is spare bandwidth inside the system, and it gives it to the remaining tenants inside the system, and it configures their queues again. So these are examples of inter-tenant work conservation. And finally, in phase 5, half of the VMs, so 15 VMs from each of the tenants, remaining one, the blue one and the yellow one, they go idle. There is an initial drop in performance, and then the controller notices that there is spare capacity left over, and it then again configures the queues for each of those VMs. And this is an example of intra-tenant work conservation. So we met the SLAs, and now the question is, what about the overheads, the penalty for doing so? So first we look at data plane overheads at 40 gigabits per second. In the previous experiments, they are negligible. So to bring out the worst case performance, we ran a different experiment where we vary the I/O sizes from 512 bytes to 64 kilobytes. 512 bytes, the throughput might appear small there on the y-axis, but it's actually in IOPS. It's actually quite large. It's about 500,000 I/O requests per second. The main takeaway here is that the performance overhead, even at these high speeds, tends to be negligible between the original system and the one where we have the queues added for the performance SLAs in place. So finally, we look at control plane overheads, the network and CPU in particular. So in this example, the controller is going to configure queue rules and then subsequently receive statistics and updates the token rates every control interval, which is 1 second in this particular case. On the y-axis here is the number of flows created. So we see, for example, that at 10,000 flows here, you need around 2 megabytes worth of network traffic to just create the flows. That's the dashed green line. Subsequently, once you have created each of these flows, maintaining statistics for them and then updating the token rates consumes very little bandwidth, so 0.4 megabytes per second, respectively. So again, the overhead is small along the control plane. And furthermore, at that 10,000 flows per second range, the CPU overhead at the controller is minimal, 0.3%. I'll conclude here. So in summary, we've defined and built a storage control plane. We have controllable queues in the data plane, and we also have the interface between the controller and the data plane, which is the IOFlow API. We've built several centralized control applications to demonstrate the power of the architecture, and we're looking into how this would work for public clouds as well. There will be a demo at the poster session today. Thanks.
All right, well, we will take some questions from the internet. So one question is, how do you deal with latencies in a flow-based model? Is that
with latency?
Yeah, latency, SLA.
So currently, we have priorities inside the system. So priorities are proxy for latency right now. We don't have a latency SLA as such. So a tenant that might want good latency would just set higher priority for its requests.
So Eric Heide, University of Utah. Since I don't have any competition, I'll take 2 bites at the apple. The first is that I don't quite understand when a rule matches, when you say next hop, do you say the stage, or do you get to say which queue it goes into at the next stage?
That's a good question. Whenever a request matches for the next hop, you get to say the stage, which stage does it go next.
Okay, but you don't get to say.
And then the next stage will have a controller rule that will specify those requests that are coming to that stage, which queue they will go next.
Okay. I'm still want to take my second bite. Can I do it? So the performance results that you just showed on slide 30, if I understand, those are against RAM-based storage.
Yes.
Do you have data that shows what it looks like against disk-based storage, which
Yes.
would have more variable? Can you characterize those results?
We have data in the paper. As I was mentioning, we just chose RAM disk for this presentation. In the paper, there is results for both SSDs and disks, and they are qualitatively similar. The overheads are obviously smaller.
Okay, I think in the paper, the only data that uses disk storage is performance overhead?
Performance overhead along the data plane, yes.
Right, so anyway, I'll come to you later for the throughput guarantees on the disk.
Okay.
Okay, thank you.
Roger from CMU. I guess at each level, I guess the component needs to know the ID or the relationship of what requests correspond across the levels, right? Do you find that how do you guys deal with aggregation events, right? Do you find that limits the types of aggregations you can do, or I'm imagining that you have a bunch of things that are being aggregated and they have different priorities, for example, or different SLA requirements. Does that happen?
So for the kind of examples we haven't had any aggregation in place. If there is aggregation, we do similar techniques to the SOSP paper in last SOSP 2011, where you have some of the flags basically tainted, either that or avoid aggregation in the first place. And they showed, I remember, in SOSP that those were sufficient to deal with it.
Cool. Can I do one more quick question, or one more question?
Peter Disnoyers, Northeastern. In the paper, it seems that all of the modifications for IOFlow were in actually OS storage stacks. So I'm wondering what your thoughts are on, what would be needed for some data system environments where that doesn't cover the entire storage path.
You're right. One example, it doesn't cover the entire storage path, is block devices. In fact, we don't have currently, we haven't implemented yet any block layers inside the system. Again, there was a paper in SOSP last year, the same paper in fact, that dealt just with that part, just with the block device itself. So they added a command to the SCSI protocol to just deal with that. So we could leverage similar techniques in that particular case.
Thank you.
So just one more clarification question, I guess. Did you guys find that for the cost models, do you have one cost model per layer in the system, or do you have like one integrated cost model at the very top? Because I can imagine going both ways, right?
So the controller allows us to build these cost models both close to the device, but also close to the source wherever they're actually used.
Mm-hmm.
So both cost models can actually be provided. Obviously, for the queue and the hypervisor, you want to give them that particular queue, the cost model that it sees. So it would get the cost model for the request coming from the hypervisor, basically.
Okay, so you have cost models at every level, basically.
Yes.
in your source. Okay.
Great, let's thank the speaker.